last 10 minutes by setting up the way of solving inhomogeneous wave equations. So we've talked some about homogeneous wave equations, okay? But you can imagine if we motivated this with the physics of a string, we could have a string to which you're applying some external forcing on the interior of the string, you know, not just the boundary or something like that, okay? So we're going to look again at just the half plane. So we're going to live on the real line with our initial conditions. And just for simplicity to start, we're going to have homogeneous initial conditions. So the dynamics of the string is totally determined by the forcing that it's receiving, okay? And if you think back to your differential equations, like ODE classes, maybe you remember the method of variation of parameters for solving systems of inhomogeneous differential, you know, linear equations, ordinary differential equations, okay? So this is sort of related to that, okay? So the way to solve is using this formulation called Duhamel's principle, okay? And as I said, it's related to variation of parameters, okay, for ordinary differential equations, okay? So it's really driven by this geometric interpretation of the different regions of dependence for a particular point in your solution, okay? So this particular point in the xt plane, call it x0, t0. Remember, this has some domain of dependence, right? Where the only things that determine the solution here are given by the values of the solution or any forcing that's applied in this region now, okay? And we're going to use some Calc 3 in this derivation, so we're going to be talking a lot about normals. But the idea, okay, is that if we look at the boundaries of these regions and we sort of trace a contour around this region and call this line segment here I, this or 1, this one 2, and this one 3, okay, we can get at essentially the total influence on the solution at this point here by just looking at the value of the solution and the forcing along this contour, okay? So this kind of starts by noting, okay, that this operator here, I can write as a gradient, okay, or a divergence taken over the x direction derivative and the t direction derivative applied to c squared ux and minus ut, okay? So I've flipped the sign convention there. And so, yeah, so this is equal to c squared uxx minus utt, and this is equal to minus f of xt, okay? So if you remember back to calculus 3, the idea that I'm, you know, taking this domain of dependence and I'm associating with it, you know, the contour boundary that's drawn around it, okay? And I'm writing down a divergence here to sort of set up this method. You might expect that I'm using a particular theorem from Calc 3, okay, that involves a divergence. in particular the divergence theorem, in order to interpret the impact of this domain of dependence on this point here. Okay, so essentially, what does the divergence theorem tell us? I'm just sort of sketching this all out in words for now. Okay, but the outward flux, okay, is equal to the volume integral, okay, inside, okay. And so in order to characterize the volume integral that's going to determine the solution here, I can just look at the outward flux from this region, okay? So, and when you're talking about outward fluxes, right, we need the normals of each of these parts of the contour, right? So the normal on this region, okay, or sorry, on this contour is going to be 1 C multiplied by 1 over square root of 1 plus C squared, okay? This normal here is going to be minus 1 C times 1 over square root of 1 plus C squared. And this normal down here is just going to be 0 and minus 1, right? Because it's just points vertically down there, okay? I can label these points too, right? This is the line here, if I'm tracing all the way back to t equals 0. So this point would be x0 plus ct0. This would be x0 minus ct0 here, okay? And now I've characterized all the points on this diagram, okay? So where am I going with this, okay? Well, what I want to essentially do is I want to take the volume integral of the original PDE, okay? I have to be able to compute that volume integral, okay? And the way that I'm going to compute it is I'm going to use the divergence theorem and the fact that I can define the normal derivatives along this contour. I can define the value of all the relevant functions along this contour. And the contour integral will be easier to take than trying to take the volume integral over this domain of dependence, okay? And so Duhamel's principle depends on a few insights. First of all, it depends on, this knowledge that a solution at a particular point is only dependent on a, finite subregion of your domain that precedes that point. It's bounded by, the characteristics that propagate out from that point. And just this little bit now that we can use vector calculus essentially to help us compute the integral that's going to give us, how this domain of dependence translates into the solution at this point. Okay. Why do we have to go to all this trouble? Okay, well, because once you introduce an inhomogeneity, this inhomogeneity could really have, it could have any form you like, or, you'd like it to be the most general function. Okay. And so you can't just use D'Alembert's formula anymore, okay? Because that relies on really just having the value of a solution at a very particular slice in time or a slice in space. Now that the forcing is, could be different at all different points, you need to be able to sort of add up all those effects. And the way that you do that is by performing this volume integral, okay? So we'll get into the nitty-gritty of that on Wednesday. Before we stop, are there questions about the lecture? I'll hang on for office hours questions too. Okay. So that's, yeah, so we'll continue that on Wednesday. And yeah, for now, I'm happy to take any homework questions or other general questions that you might have for those of y'all that are sticking around for office hours. Otherwise, see you on Wednesday.
Thanks, Zach.
Yeah, thank you.
I have a quick question about this last part of the lecture. So if the initial conditions are not homogeneous, would the way to do it be you solve with Duhamel's principle using forcing with homogeneous conditions and then one with no forcing and the inhomogeneous conditions?
So you can do it. I mean, it would just be that when you trace all the way back to here, right? Then you have to worry about your initial condition just along that contour, okay? But it just creates more of a mess when we're doing the derivation. We're just going to do it with, yeah, homogeneous initial conditions first, and then we can sort of infer how to do it once we have inhomogeneities there. But yeah, but it would change what the line integral along this contour is. Yeah.
I had a quick question about the lecture video.